Yeah, totally. It's just not maybe the most fresh stuff in the world. So like you saw this, but maybe it wasn't the last thing you saw last year. All right. So measures of position. We talked about standard deviation, and so what we're going to start doing is thinking. We're going to think of numerical values in terms of their distance away from the mean. All right. So standard deviations would represent the scale or the ruler that we would be using to represent a value's distance away from the mean. Right? So I wouldn't say anymore that you have a 90 average. I would say that you're one standard deviation above the mean. Right? So you're a +1 or a +2 if you're running a 100 average. Right? Because if we're thinking 80-10, 80 is the mean and standard deviation as 10, and then that would be consistent. All right. We want to normalize because the way the world works is it follows a normal distribution. And if the data set, you might look at it, I said this yesterday, you may look at a data set and say, well, that's clearly a skewed data set, but I can convert that data set into a normal distribution and then draw some conclusions and then convert the data back later on. All right. So if we learn everything there is to know about a normal distribution, we could draw lots and lots of conclusions. And the first thing is the empirical rule. It's the 68, 95, 99.7 rule. All right. So if you've ever seen a normal distribution, you've probably seen these values. All right. So I'm just going to just off on the side here, just draw a quick sketch of a normal curve. Best I can anyway. I'm going to put an X bar in the middle. And then 1, 2, 3 tick marks to the right. 1, 2, 3 tick marks to the left. All right, so we're going to increase the mean in increments related to the standard deviation. All right, so extreme close-up. So X bar plus 1s, X bar plus 2s, X bar plus 3s. And we'll do the same thing going in the opposite direction, just with minuses. So X bar minus 1s, and so on. Back in. All right, and so what the empirical rule is telling me is that about 68% of the data will lie within one standard deviation of the mean. So I'm going to draw little benchmarks here. There's one. That's a little off. Let me do that again. Good enough. So this region here would contain approximately 68% of the data. All right, we're looking at about 95% of the data within 2 standard deviations of the mean. So that's what I'm illustrating now. Made it a little thing, whatever, it's fine. About 95% of the data. And then the rest of the data, well, it goes out to infinity, so the rest of the data, the 100% of the data, you would never be able to truly capture. So the best we could do is get really, really close to 100% of the data, so 99.7%. And so that brings us out one more step. So I'm going to go below. And so this interval would capture about 99.7% of the data. All right, so about 99.7% of the data would be in that interval. All right. So it's telling us that the majority of the data will be within one standard deviation, majority being more than 50%. Most of the data is going to be within 2 standard deviation, and damn near all the data is going to be within 3 standard deviations. All right. So bottom line is, once you go out 3 standard deviations away from the mean, you've captured pretty much everything. So it's a question of, do I want to keep going out? Do I want to keep expanding my interval? Probably not, because I'm not going to capture much more data. The approximate values, because statistics can be a little wishy-washy. So when I say approximately or about, it really kind of sort of just means that, right? So if it's near 68%, if it's near 95%, if it's near 99.7%, and then you say, well, what's near? And I say, if it feels like it's near, it's near. And then you say that's not good enough. So I just made up a rule. Plus or minus 2%. That's what we're going to go with. Because over the years, people are like, this whole it feels like it's close enough, that's not really doing it for me. So we need a number. So 2%. And then, of course, there's somebody like, well, if I add 2% to 99.7, I get more than 100%. Well, yeah, okay, cool. Thanks for pointing that out. And then that's the end of it, right? So give or take a couple of percentage points. That's all we're looking at here, all right? The visual is probably the most important part. When I put in a data set, I don't do any calculation to make a determination of normality until I've looked at the graph itself, right? If it's not a symmetrical graph, I'm not even bothering, right? So what does that mean? It means that you could look at a box plot, a histogram. You could, I suppose, make a stem plot, but I don't know that that's really going to add too much to the narrative here. But and also we haven't really gone over those, so it's kind of like a little iffy. But a histogram and a box plot on your calculator, you're definitely well qualified to do. So let's take a minute and pop this data in our calculators. So stat edit. So we have to do a few things here. I mean, the question is telling us to use the empirical rule to make a determination, but I would even stretch that out further by saying, all right, you're taking the AP, you're taking one of my tests. You might just say, determine whether a follow represents a normal distribution, justify. All right, if that's the case, you always start with the diagram. All right, so I'm going to do second y equals. I'm going to look at the box plot. I'm just looking for symmetry. Symmetry does not prove normality. Just because a data set is symmetrical does not mean it's normal. But if it's way out of whack, then you could probably make a good case that it's not going to be a normal distribution. So we're going to get a good sense going in of what we're up against. All right, so I'm going to enter on plot 1, turn it on, not the modified. All right, so hit down and go to the one that looks like an ordinary box plot. Now I have a frequency table. I have data values in L1 and L2. So my X list is in L1, that's correct. L2 should be my frequency list, so second 2. All right, I don't know why it does this. Some of the calculators do, some of them don't. It has the alpha lock on, so if I hit zoom, it's gonna bring me to a different menu, and it's just really annoying. So if you ever see the alpha lock on when you're in here, just hit alpha again to turn it off. I don't know why that's a default setting. It's just so weird. All right, we're going to do zoom stat, zoom 9. All right, it looks symmetrical. you can hit trace to find where the median is. Now, the median is a little asymmetrical, so that might be a little bit of an issue. But overall, the distribution is symmetrical. You have equal parts on the high end and low end, right? So it's kind of like our license to say, all right, we can continue with this. If this were skewed extraordinarily in one direction, then I would say, well, forget it. I'm not going to use the empirical rule because it's not going to show a normal distribution, all right? So let's quit out of here. We're going to do stat, calc, option 1, L1, L2, and calculate. All right, I need the mean and the standard deviation. All right, I'm going to make a note of them, but I'm not actually going to type that number in. I'll show you what I mean by that in a minute. So X bar is approximately 18.829. S is approximately 2.144. All right, and so we're going to compute a few things because the first rule tells us 68% of the data will be within one standard deviation of the mean. All right, so what that's telling me is X bar plus or minus 1S. So I got to figure out that. That's one standard deviation about the mean. I need to verify that that's actually going to contain 68% of the data without retyping all that crap. All right. So the calculator is a substitution-based calculator. So everything that is displayed here is showing us that X bar, that symbol X bar, has a stored value of about 18.829. All right, so what that means is if I could find X bar in my calculator somewhere and hit enter on that, it would bring up that number for me. All right, so that's what I'm going to do. I'm going to quit out of here. In the vars menu, and I'll jot this down this one time. Then after this, you're going to be on the hook for it. So it's in the vars. And then go down to option 5, which is statistics. And then you can see all of the symbols that were used in that stat calc 1, right? X bar and S is really what I'm looking for, all right? So I'm going to type X bar minus, I'm going to type in the 1 times, because I'm just going to do a little second enter business to manipulate this. So I'm going to go back into it, vars, option 5, and then bring up SX. All right, since I ran stat calc 1, it stored those numerical values, 18.829 and 2.144, it stored them in for X bar. If you want, just bring up X bar and hit enter, and you'll see that it's 18.829. All right, but I'm going to hit enter. Then I'm going to either hit second enter to bring up the calculation again, or you could just do the up arrow a couple of times and hit enter. So we're recalling, make the minus a plus. All right. So aside from just the one time writing down approximates for X bar and S, I was able to actually work with a full-blown decimal in my calculator and not sacrifice accuracy. All right. So I'm looking at an interval of about 16.686. To 20.973. Okay, so what I need to do is determine if about 68% of the data falls in that interval. All right, so I'm just going to count up the number of values that fall between 16.686 and 20.973. All right, so I'll just ask you, does 14 fall in that interval?
No.
What about 16?
No.
No. 18?
Yes.
Yes. 20? 22?
No.
No, so we're here in this interval. We're looking at these values. How many values am I talking about?
27.
27 out of a total of?
41.
27 out of 41, which is approximately, if you round it, 66%. All right. So it's like in that gray area though, because maybe you'll say, or, you know.
It's within 2%.
Yeah, I mean, you could even say 65.9%, in which case it would not be within that arbitrary 2% that I came up with to represent approximate. All right, so it's like, well, what are we talking about here? I don't know. Is it going to work? Is it going to be a normal distribution? The answer is maybe. All right, this is like right on the borderline. You could go either way. Some people write the 66% and say, yes, it checks out. Some people say 65.9% and they say, no, it fails. All right? All three conditions have to be met in order for it to be a normal distribution. All right? So we have to go the distance here and see if all three are going to work. So let's do x bar plus or minus 2s. Good news is the hard work's done. Back arrow or up arrow, grab, oops, sorry, overshot the mag. Got that guy, make the 1 into a 2. That's why I put the 1 there to begin with, so I wouldn't have to insert anything. And then make the minus into a plus. So this interval, gotta put my pen on, 14.542. 23.117. All right, so I go back to my raw data set. I'm going to count up the number of values that fall in that interval. 14's not in that interval, neither is the 24. So we're looking at these entries. All right, which is how many? 39 out of 41. So 39 out of 41. Talking about 95.1%. So that seems to check out. If anything, if you were on the fence with the first set of calculations, you're like, I'm not really sure. This is starting to confirm that it's starting to look like a normal distribution. All right, so now we just have one more. Anything in the neighborhood of 99.7 is going to get the job done. So x bar plus or minus 3s. So we're going to write the interval down, even though at first glance we know it's going to capture all the data. For the appropriate work to be displayed, you have to write it down. 398 and 25.26. Well, it would be 260, so 26. All right, so it's 41 out of 41, which is 100%. And it's very close to 99.7. So therefore, normal distribution. All right, so we used the empirical rule to justify a normal distribution. Graphically, we knew it was symmetrical, but did it have the right shape? We weren't sure, so the empirical rule fleshed that out for us. All right. So the question becomes more so, what are we going to use this for? And that's a different conversation for a different day, but we'll get there. All right, we do have to talk about z-scores. Z-score is, when I was talking earlier, about the fact that standard deviations represent the spread of the data, and we'll start thinking of individual scores in terms of how far it is away from the mean. So if that's the case, then we could define that idea as a z-score, all right? And so every person every test score, every individual data entry can be represented based on its distance away from the mean, also known as a z-score. So all we're doing here is identifying z-scores. The reason behind it is if I give each one of you a z-score based on your performance on a unit test, then I can compare all your data to one another. Right? It becomes a whole lot easier that way. So, very simple calculations. We have x sub I minus x bar over s. So we have two individuals, Michael and Jane. So Michael got a 75 on his test, Jane got something on hers, cut off. So the mean in Michael's class is 73, the standard deviation is 7.2. All right, so for Michael, we're going to have a z. His individual score was 75. His class average was 73. Standard deviation was 7.2. So Jane got a 73, right? And her class average was 71 with a standard deviation of 6.3. All right. So Z would be 73 minus 71 over 6.3. All right, so both had the same exact deviation from the mean, but since Michael's class is more spread out, that's going to impact his standing in the class compared to Jane's standing. So 2 divided by 7.2, we're talking about approximately 0.278. And then for Jane, 2 divided by 6.3, we're talking about 0.317. All right, so the question was, which of these two students scored better relative to their classes? Well, Jane did. Jane performed better relative to her class. All right, so we know that Jane did not perform better. Her score was lower. She got a 73, he got a 75. He performed better, but she performed better relative to her class. All right, so what are the two classes? It really doesn't matter. You could be talking about same grade level, but two different courses, stat versus calculus. But you could also be like, okay, well, you have a student in Algebra 1 and a student in multivariable calculus. All right, so if a student got, I'll just say without even talking about like too much in terms of the data, if a student got a 75 on a test in Algebra 1 and another student got a 75 on a test in multivariable calculus, who knows more math? Multivariable calculus. Aside from the obvious things like you had to get to that course to begin with, it's harder content. So to get a 75 in an environment where the content is that much more difficult would be more challenging. So, you know, that's kind of like an everyday explanation for it rather than just a mathematical one. Right? But that's something that STAT gives you that some other classes may not, because you can conceptualize this to the everyday. All right, usual, unusual values. The value is considered to be unusual if it's beyond 2 standard deviations around the mean. All right, so it's very easy to compute. The problem that people run into, and so it's gonna involve studying. It's as simple as that. You're gonna have to study. All right, I know maybe some people weren't planning on doing that this year. And that's okay, that comes out in the wash. But what happens is, unusual values, I mean, you look at the computations, it's not difficult, we just did it, all right? But people get it confused with outliers. So I asked for unusual values, and you give me outliers, you lose full credit, all right? Or vice versa. So you gotta know what the terms are, otherwise it's all over. So they're telling us here that the mean is equal to 72 and the standard deviation is equal to 4. and we're making a determination of whether 59 is unusual. We don't need fancy calculators for this because x bar plus or minus 2s is pretty easy to compute. 72 plus or minus 2 times 4. So 72 plus or minus 8. So what was that, 64 to 80? All right, so that's the usual interval. So the usual interval. All right, these are the ordinary values. These are the ones that you would expect to happen. All right. Yeah, anything outside of this interval would be considered unusual. So therefore, 59 is unusual. After every test, for better or for worse, I always share what the mean and standard deviation is so that you can figure out what the usual range is and then see where you are in relation to that. The for better or for worse part, the worse is when you find out that your score was unusually on the low side. So it's like, that test was too hard. That was so unfair. I hate that teacher. He's a jerk. And then you find out that the data does not support that. It's just you. You're the only, you're the problem. You know, so no, I don't do that to hurt feelings. I do that so that you have the information. But and honestly, I kind of like the jolt when a student realizes that they were unusual on the high side. You know, that's a good feeling, you know. And then some people just walk away being like, okay, I'm usual, ordinary, not extraordinary, just ordinary. Just a run-of-the-mill stat student. Got stuff right, got some stuff wrong. Life goes on, the world's still spinning. So, but data drives a lot of things, so it's important that you at least try to evaluate that data. But I always get a kick out of it because, like in here, we know what usual and unusual values are. So after the first test, we could all have a good laugh at the person that when I say the class average was an 82 and the standard deviation was 10, the person says, oh, 82, that's so low. And that, like, we can all laugh at that person because what that means is that they don't understand the concept just by making that comment. So we'll have a good time, you know. And here's the thing. It's so important that even if you yourself don't understand the concept, you also have to laugh. All right? Because otherwise you're outing yourself as a person who doesn't get it. And that's a tough spot to be in. But just as a quick refresher, 82 and 10, that's perfectly beautiful because if I add 2 standard deviations to 82, what would I get? 102. So it's not unusual to get a score above 102. I like the sound of that. That means hundreds in the usual range. That works for me. All right. 2 standard deviations below the mean would be what? 62. It would be unusual to get a score below 62. Below, like squarely in the failing range. Yeah, I would like that to be an unusual situation. Yeah, and so would you. So if you didn't get the explanation, or if you didn't get the concept before, that explanation, hopefully you do now. The following data can be considered a simple random sample of ages of NFL players as of June 2019. I feel like I just made up the data set and then threw in Drew Brees' and Tom Brady's ages or something at the end. That seems right. All right, anyway, determine any outliers and unusual values for data set. Explain the meaning of each in the context of the given situation. All right, so right to the calculator, stat, edit, get rid of the data. So remember, clear on your column headings to get rid of the data. And then try not to lose count. Might want to make a frequency table, but I've already started going down this road, so I'm just going to continue. I screwed one up. All right, pretty sure I just typed it in all correctly. If not, we'll find out in a minute, I guess, when we all have different answers. All right, so let's start with outliers. All right, determine any outliers. All right, explain the meaning in the context. So at no point did it say, show how you arrived at the outliers. All right, show all work, show all calculations. So this question is just asking me to state essentially what the outliers are, to determine what they are numerically. All right, so what do I do? Tell me what I do in my calculator, a nice shortcut approach for finding the outliers. This is like the highlight of my life here. Sorry.
You can graph it using a modified box plot.
Absolutely. Absolutely. All right, so second, y equals, hit enter, put it on the modified plot. Now, this part may vary from person to person. I put my data in just in L1, one raw list. If you made a frequency table and put it in, then you could leave it from the settings from the previous question. But I have to change my frequency back to a 1. All right. Again, the alpha lock, it's so annoying. I don't know why it's like that. So I'm going to hit alpha so that when I hit a 1 comes up. All right. Because otherwise it'll bring up the letter Y, and that's just annoying. All right. Best way to come up with a graph, once you have the information plugged in and all the settings, do I just hit graph or do I hit something else? Zoom stat. Zoom 9. And what about this graph tells me that there's an outlier?
It's not connected.
Yeah, it's not connected. There's a dot there that's not connected. How do I find out the value of that dot?
Click on trace.
Click on trace. Now, since it's the rightmost dot and there's only one of them, you could probably assume that it's what? 46, all right, because it's the largest value. But for the satisfaction of having it confirmed, it is 46. For the sake of having supporting work, because sometimes, you know, even if you're not required to, you want to. Like you, right now, might not think that you want to show work, but you will, because if I tell you a question's worth 3 or 4 points, and you put down the wrong answer and you get nailed for full credit because it's wrong, and the reason why it's wrong is because you just typed the data into your calculator incorrectly, you want some way to kind of recoup some partial credit. So I recommend you give me something, and that something could be used modified box plot. So tell me what you did to determine your outliers, and that's good enough for me. Because at that point, let's say you put down 47, and then you told me you use a modified box plot. I'm reasonably confident that you got the 47 because you accidentally typed 47 instead of 46. All right. So, like, as long as I could point to the mistake when I'm grading your work, then it's only going to cost you 1 point. If I can't point to a single mistake, then I got to get you for more credit than that. All right, so give me something and it'll generally pay off for us. All right, so now let's get some one variable statistics. So stat, calc, 1. My data is still just in the 1 list. So I'm going to clear out my frequency list L2. Alpha lock again for some reason, so let me unlock that, hit the alpha key, and then just type the 1. Hit go 2 because what did I do? Oh, you want to, this is the one where you want to leave it blank for some reason. consistency. You'd love for that to be a thing, but apparently it's not always. So enter. Now you have these values. So for unusual, bless you. We're going to note what the X bar is. It's a clean number, 31.25. Average age of the randomly selected NFL players is 31.25, with an S of about 6.34. Right, so unusual, I only care about X bar plus or minus 2S. All right, it's not a beefy calculation by any stretch for you to do it out, but you want to get in the habit of being able to navigate through the different functions in the calculator. So, yeah, I could type in 31.25 plus 2 times that, but let's learn where to find this stuff. Vars, option 5, X bar, minus 2 times vars, statistics, option 3. And sometime, maybe the end of this week, maybe next week, I'll show you how you can write this in as a program. So it'll do it automatically for you once you input the data. All right, so hit enter. We got the low bound. Go back, grab it, change the minus to a plus. Now we have the upper bound. All right, so we're looking at 18.5. So it would round, if we're going to 3 significant, it would round to 2 decimals, so 5.7. And 43.93. So therefore, in terms of unusual values, we have nothing on the low side, right? But on the high side, is it just the 46? No, it's also 44. So 44 and 46 are unusual. And, you know, like you could get more specific. You could say unusually high, but I feel like that's asking for trouble. Because sometimes, I call it the basketball scores versus golf scores. Sometimes a high number is not a good thing. You know, so the interpretation of it, if you're just looking for the size of a number and what that means, is sometimes that you can draw the reverse of the conclusion that you're supposed to, so it's dangerous that way. All right. So that'll do it for today.